Go back a little step and talk about the E2 briefly, so we can move on and talk about the E1, and also think about the competition, because I know Tyler has said this in the SI session. I'll say it in recitation. It's about to get very complicated because nothing is as clean as we've seen. Nothing is just going to give you one product. Usually you're going to get more than one product, be it stereoisomers in an alkene cis and trans, be it R and S in an SN1 reaction, or by the end of this week, SN2 competing with SN1, competing with E2, competing with E1. Right? Where does it go? So you can see it's going to be more challenging, and hopefully we're in good shape for that. So what we've talked about in terms of chapter 8 so far is stereochemistry of alkenes, basic structures of alkenes, and also the one reaction in which we took an alkene with a leaving group. And the problem here is that the base is too big and the molecule is too crowded to do an SN2 reaction. The overall motivation for this type of process, I always think, is this. The reason these reactions want to happen is that this species here is reactive. It's usually O-, something like that. It's a strong base or a strong nucleophile. And you want to transfer that negative charge and its instability onto the leaving group, whatever that leaving group happens to be. If it's a Br-, it's a big ion, it's good at leaving. If it's a sulfonate, like an SO3-, it's good at breaking off because of resonance. So what happens in the meantime is that the organic material has to get involved, and we have to think about the possibilities of this breaking apart or not, happening at all at the same time, and forming alkenes. It's a very, very useful way of making alkenes, which will be useful for the rest of the term and also next term. So we have two possible ways of doing this, like we had for the substitutions. We have the SN2 and the SN1. One was concerted, one was stepwise. Depending upon the conditions, depending upon the solvents, depending upon the substrates, and today the pH, we'll talk a lot about pH, you'll get one pathway or the other, either concerted or stepwise. And most of what we'll do this semester will fall into these two pathways. Okay? And most of it will be polar, most of it will be ions. Now at the top, we have the possibility of everything happening at once in an elimination process. How do you know it's elimination? Well, you study and you recognize that these conditions don't allow for the SN2 because that substrate is tertiary and it's too crowded to do an SN2, so it has to go someplace else. And that gives us the E2. Now, what we'll do today and Wednesday, and I plan on taking the rest of this week for this chapter because it is heavy, and then 9 is really heavy. 9 is the heaviest of the semester. We'll take our time and we'll develop these ideas so it starts to sink in. We'll look at the stepwise pathway, which we'll call the E1, and that's in a system in which there isn't a very good base around. The base is not strong enough to attack that molecule. So that fits with the SN1 because in the SN1, the nucleophile wasn't very strong. It allowed other things to happen, and those other things would be carbocation formation. In this sense, we'll talk about E1, but again, we're going to see that this allows for formation of an alkene, and this gets very complicated. Why not do an SN1? Well, we'll see competition between two of them. Now, to do the E2, we looked at the possibilities of doing some experiments like we did with SN1 and SN2, add more base, add more substrate, what happens to the rate of the reaction? In this case, it will increase in both cases. That's because the rate determining step, there's only one step in this reaction so far. The rate determining step requires both the substrate and the base to be there to get this reaction to work. So it's going to be bimolecular, and it's elimination, so we'll call it E2. It is completely parallel with the SN2, right? That will start to be, I think, make more sense in a few minutes. Are we okay over there? Yeah. Okay. Now, this mechanism is really the fourth of the semester that you've seen. You saw acid-base chemistry, you saw the SN2 and the SN1. Now we're talking about the E2, by the end of this week, the E1. And this now requires bases, and you should recognize what a good base is from the acid-base chemistry that we did months ago. And you should recognize tertiary systems are crowded, they can't be attacked in a substitution process, so we see this taking over now. We did mention briefly before the exam, and this mechanism wasn't on there, it'll be on the next one. Exam 3 is, we've gone past the withdrawal date, we're left with the people who should be able to pass. Exam 3 is challenging to say the least. So now we've got to think about the conditions for this and how it can work. You've got to start looking at these substrates critically. You've got to think about what can happen, what will happen, what won't happen. And what we'll see now is that in this system, it looks an awful lot like an SN2. And if I get more detailed, which I have to in the near future, and I'm going to put in things like a solvent, I'm going to put my phone down, and we're going to start talking about the mixture of the two. How do you tell which is which? Now, for this example, if I put DMF in there, as of last week, before the test, if people see DMF, they're looking for something to tell me, okay, SN2. And that wouldn't be correct anymore. Why can't this do an SN2? It's tertiary and it's too crowded. See how it all comes together? And you can't forget stuff we learned in the past. So in this example, we have a tertiary alkyl halide cannot do SN2. It would love to do SN2, right? That nucleophile, can you describe it as strong or weak? That's a strong nucleophile. It wants to attack something, but the problem is the carbon that contains the leaving group, the alpha carbon, is too crowded. And so this has to go someplace else, and where it goes is for the beta hydrogens. So I have a hydrogen here, and you'll see now in homework 8, I'll try to sort of push you towards thinking about this. I have options. Are those protons the same as each other, or are they different? They are the same in that instance. You only get one product because you can take off either one of those protons, and it gives you the same product. But again, the motivation, the driving force for this thing to happen really is to get this O- to become stable, which it does when it becomes its conjugate acid, and for the Br- to take over that negative charge, because Br- is way more stable than O-, and you know that from pKa's. You know that from stuff from acid-base chemistry. So think about this one. Only one possible product. In this case, it's secondary. Secondaries are always an issue here, and it will really mess things up in a few minutes when I tell you for the E2 reaction, primary, secondary, or tertiary can do this. So far, it's been fairly clean. We said SN2 was on primary systems and methyl. SN1 was on tertiary. That was a nice divide. Okay, in this chapter, no, we can't do that. We now say that this is going to be E2, not because of this being a secondary halide, but what do you know about this stuff? It's large, right? It's very large. And so it's not going to be able to attack as a nucleophile. And what we're going to find now is that acid-base reactions are fast because the protons we're attacking are generally very accessible. If they're accessible, your base/nucleophile will realize, can't be a nucleophile, too crowded, go someplace else, go for a beta hydrogen, less crowded, lower energy pathway, faster reaction, and that gives you the E2 outcome. So think about other systems. We have to worry about isomers. A lot of what we'll do today is to talk about the isomeric outcomes. Why do you get single isomers in some instances and multiple isomers in others? Very complicated. In this example, what type of alkyl halide? Tertiary. What type of this? Strong base, weak base, strong nucleophile, weak nucleophile. Strong at both, right? It's a powerful nucleophile and a powerful base. Why can't it simply do SN2? Tertiary, too crowded. So what we'll do instead, and notice this is not a very big base, right? It's the halide now that's the crowded part. So you've got to be careful. What we're going to look for here is beta hydrogens. It can only be these two, either here or here. If you go further out, you can't make a pi bond. And so now we'll talk about this in a concerted process, and that will give us alkene here, which is this one, and it will give us an alkene here, depending upon which one you go for in different molecules. What we need to do now is start talking about rules that govern how this happens, observations that people made to tell you that, okay, in this system, I'm going to get more of this because da-da-da. You get more of the one on the left. Any ideas why? It's tetra-substituted, right? So it's a wee bit more stable than the one on the right because it's more substituted. You've got more alkyl groups pushing electrons in, therefore stabilizing sp2 carbons. So we'll have to worry about something called regioisomerism now, where the reaction takes place to give you multiple isomers. So with that in mind, this is the first slide of the new stuff. I take my time with this because for those who are on the borderline, I've got a huge number of C's in this class, and a huge number of those people are on the wrong end of a C. They're in the 60s, not the 70s, right? And I need those people to get through this class by putting the effort in now and taking our time to make sure we understand this so it doesn't get completely out of hand. If you look at these systems, they do look an awful lot like what you've seen in the past. You've seen this one at the top. This is the competition now between E2 and SN2 because let's face it, a nucleophile can be a base and a base can be a nucleophile. And you have a leaving group in both reactions, the SN2 and the E2, so what's going to happen? In this case, what type of alkyl halide? Primary. So what can you tell me about that? Carbocation any good or no? No, so please don't draw primary carbocations on exams, thank you. What's going to happen faster? The nucleophile attacking or the leaving group breaking off first? Nucleophile attacking. Now in this instance, you get a very high yield of this. This adds up to the sort of simple, typical, very, very good SN2 process. You don't see much of any E2 here. You've got to add up things here. You've got to make sure this makes sense. In this example, this is accessible. It's very easy to get to. Yes, you have a good leaving group. Yes, you have the solvent required for an SN2, DMF. But you're also swapping, in this case, Br- for O-, which is the motivation for the reaction. What we'll need to worry about now is the relative stability of alkenes versus the substitution product. Now, let me say that again. We have to worry about the outcomes in terms of their relative stabilities and also how fast they are formed. Which do you think is more stable, or is worth more energy, or stronger? Do you think it's a single bond or a pi bond? Say again? A sigma bond or the pi bond? Not double bond, I'm not going to say double bond, the sigma bond or a pi bond. Do we know this? Which is more stable, the bond between C and O or the pi bond between C and C? The sigma bond. The sigma bond. If you don't see that, write it down. If you don't understand that, write it down. A sigma bond is more stable than a pi bond. And I'm not saying double bond because a double bond is different. A double bond is a single bond and a pi bond. I'm talking about the pi electrons that are the second line in this double bond. So I want to be careful here. This product is probably more stable than these products because of the fact that we have single bonds instead of a pi bond. That's a general idea. You'd rather have single bonds, or shall I say sigma bonds, formed than pi bonds, because pi bonds are weaker, not as stable. Well, in this example at the top, that is really sort of hammered home. That's exemplified, because I don't see much of any alkene. I have all the typical examples, all the typical conditions for the formation of an SN2 product: solvent, accessible nucleophile, accessible electrophile, good nucleophile, good leaving group. Everything's there for an SN2. And you'd rather perform the SN2 than the E2 because the SN2 outcome is more stable. Well, you often can't get that. You're stuck in this example down here. You get both. In fact, you get 4 different products, and you'll have to worry about major, minor, major, major, and minor, minor. Which is which? Very complicated. So in this example, what has changed? I have the same nucleophile / base. I have the same solvent. What has changed? Secondary. What does the secondary tell you compared to the one above it? Okay, this is not cations though, is it? This is going to be at E2, so it's not cations. What's different between this alkyl halide in the middle and the one above it? It's secondary, therefore it's more crowded, right? It's more crowded. So we expect the SN2 reaction to be more difficult and slower. And the nucleophile / base, because it can be both, now has other options. If going here is slow, going here can be fast because it's very accessible. Going here can be fast. And all of a sudden we get competition. The nucleophile / base just wants to get this reaction over with, doesn't really care about the carbon. It wants to become neutral by becoming the alcohol. So I'm going to say that we'll get a good amount of this because it's stable. We'll get some of this, and some of this, and some of this. Now today and Wednesday, you'll be able to decide which you get the most of. This is going to be decent yield because it's quite stable. It's got the single bond. We got the inversion of stereochemistry. That tells you it's an SN2 reaction. Now, between the alkenes, which is more stable? This one at the top, this one at the bottom, or this one down here? I can't say again? The one at the top. Why? It's more substituted. That's one reason. What's the second reason? Trans. That's it. Good. So this is going to be the major of the alkenes, and then you'll get some of this minor, and you get some of this minor. Okay? All simple ideas, but they're now starting to add up, which makes this subject very complicated. So let's look at the bottom. We've gone from a primary system to a secondary system to a tertiary system. If you look at this type of alkene, alkyl halide, it's tertiary. What can it not do? SN2, it's too crowded. So there you get a clean reaction in which you get this exclusively. You have 9 of these hydrogens that you can go after on these 3 CH3 groups, and this is a small, strong base, and it's going to be able to attack any of those hydrogens, take one off, and form the alkene. So you've got this shift from SN2 only in very accessible systems down to E2 only in crowded systems. And you're now able to say, in an E2 reaction, if I can identify it, it will happen on any of my substrates, apart from methyl. Why won't it work on a methyl group? Because you need 2 carbons to make an alkene. You only have 1 on a methyl group. So for primary system, secondary, or tertiary, you can now do the E2 reaction. And you can design a synthesis. There's something that I haven't said yet, but design a synthesis, come up with your own way of getting to a product. That's going to be coming up on this next test, the use of organic chemistry to get places and make your own stuff. So there's the background to this. Okay. This is the basically, there's your quarterback sneak, if you like, straight up the center, behind the center, and attacking the nucleophile and kicking it out. Attacking the electrophile, kicking the leaving group out. If that's not going to happen, the quarterback tends to go left or right, yeah? And you're trying to go around the end. So in this case, this is basically that, where the hydroxide nucleophile can't get to the carbon here, and so it has to go someplace else, and away we go. That's all it is. Crowding now is going to promote the elimination reaction to happen because of the fact that you can't do a substitution. So in terms of reactivity, you have some general ideas here. If you measure the rates of reaction in different flasks next to each other in reactions, you can talk about the relative rates, measure how fast they work. On the left, the primary system tends to be slower than the secondary system and the tertiary system. There's a lot behind this. There's actually quite a lot behind this. In this example, it's not an SN2, it's an E2. So it's really nothing to do with the accessibility of this guy. What is changing going from here to here? What do I need in the E2 reaction? I need a leaving group. They all have leaving groups. But what's the other requirement to do an E2? You have to have hydrogens at the beta position next door to the carbon which has the leaving group attached. So what do you think here? You've got 3 of them, you've got 6 of them, you've got 9 of them. That's going to have something to say about how fast things happen. It's much easier to find a proton here than it is over here. So that has something to say, but that's not everything. That's only part of it. The statistical idea that the more hydrogens you have, the more chance you have of attack, and therefore the reaction might go faster. But you've got to worry about the transition state now, because the rate of reaction is all to do with the height of the barrier that you're trying to go over. And this next slide is quite complicated, I think. It's trying to show that. In this example, you have a simple system like a tertiary bromide reacting with a base in an E2 process. How will we know it's E2? Add some more base, it goes faster. Add some more of the electrophile, it goes faster. That's how you do the kinetics and you work this out. But now we have to worry about what's happening up here. And for the most part, people are okay with transition states. Obviously, some people, you know, it's fourth down and goal on their own 1 yard line, and it's not going to happen type of deal. But most of you have some idea about how to put these things together. Charges could be a bit better, but you know that was the first exam you had taken from me with mechanism. So overall, I was quite pleased with the outcome. This is me being pleased. We have to worry about transition states and how things are changing as we go from starting material to product. So look at what's happening here. We have development of the pi bond. That's what that dashed line means there. Okay? We have development of the pi bond. So thinking about this idea of what transition state should look like, what do you think is more stable? A developing pi bond with more alkyl groups attached or fewer alkyl groups? More. For the same reason the alkene should be more stable if it has more groups, right? So if you go for tertiary systems, you'll sense the stability in the transition state of having those extra alkyl groups there, because those carbons that are becoming the alkene are becoming sp2. They want more electron density. The more alkyl groups you've got, the better for donation, and therefore the more stabilized the transition state, therefore the lower the barrier. Colleen. The carbons always have enough electron density, and the hydrogen always has enough electron density. Typically what you're looking for here is things that are changing from positive to neutral or from neutral to negative, right? Full changes in those charges. That's really what you're looking for delta plus, delta minus in a transition state. So now, you know, complicated details. There were two factors there. How many hydrogens do you have in the starting material, and what does the transition state look like, and how can it be stabilized? Basically, the more alkyl groups you have, the better the transition state. So those two factors both lead into tertiary being fastest, and then secondary and primary. There's a look at the transition states if you're thinking about comparing them. Why is this one higher for primary? Well, you don't have as many alkyl groups. You don't have as here, you have hydrogens. They don't help out. If you go to here for a secondary, you might have one methyl group here. That helps out, stabilize the sp2 developing carbons, this one, and the more of those, the better. Here with the tertiary, not much of a difference, but enough to make a difference. And those slight differences now should be meaning something, certainly if you're heading into PChem in the future, or biochemistry, as many of you have to do. Those tiny differences make a big difference in outcomes. Everybody all right? Anybody get any sleep? No. No. Now, the Russians are coming. Basically, there are two Russians who happen to work at the same university. One was named Zaitsev and one was named Markovnikov. And they were buddies, I think. And they talked, and they did experiments and observations on alkene chemistry, which is now in every textbook in the world, and is one of the fundamental rules that you haven't seen yet, but are about to, that govern what happens here. And we're going to say that these are observations. These molecules do not do what they do because Zaitsev told them to, or in the next chapter, they're not doing what they're doing because Markovnikov told them to. Markovnikov and Zaitsev observed what they did, and they then became a rule, a general idea of what can happen in a system. So I'm talking here about this word regioselectivity. That's a new one. It needs to be in there. Stereoselectivity, we'll talk about a bit more. You talked about stereochemistry. Now we're talking about regiochemistry. Where do things happen in a molecule? So we'll talk about isomeric outcomes. Do I get more of this on the left, more of that on the right, more of this at the bottom? All based on knowing these fundamental ideas. What type of alkyl halide is that? It's tertiary. Okay, so we're now learning to sort of think critically. It's a big deal in science and engineering. Being able to use what you know instead of just memorizing garbage. I have a tertiary system. Is it likely to do an SN2? No, so we can get rid of that very quickly. If I have a strong base here, and here, and here, are those bases likely to allow my tertiary alkyl halide to collapse into a carbocation? Absolutely not. They want to get this thing over with. So now we're going to say that the more substituted alkene, is the Zaitsev product. And Zaitsev observed that when you reacted these compounds, you got more of the more substituted alkene. We're now putting a name to the actual experiments, and it works. The opposite outcome is called the Hofmann outcome. We'll talk about Hofmann elimination maybe at the end, a way of getting the minor isomer as the major isomer, switching the regiochemistry. But right now, I have two products. I have this regioisomer, and I have this regioisomer. And they differ by where the alkenes are, that's it. So there definitely are isomers of each other. Now, what's the substitution pattern on the one on the left? Tri-substituted. What about the one on the right? Di-substituted. So for the basic reason we talked about last week, the one on the left is more stable, and we get more of it. But also the transition state to get to that first product is also lower for the reason we just gave. More alkyl groups help stabilize the outcome and help stabilize the transition state. So look at this. What's happening here is that with a base here like ethoxide, we are getting 71% of what's called the Zaitsev product, or the more highly substituted one. And we're getting 29% of the other one. So when we work our way down here and we go to T-butoxide, it starts to change. Now I'm going to stop there and go back a second, just make sure we understand the first line, and then we can add this together. Tell me about the size of this thing, big or small? It's kind of small, isn't it? So it can get places. And in this case, we have a hydrogen sticking off here, which leads to this Zaitsev product, and we have a hydrogen sticking off here, which leads to the Hofmann product. Now, if you have a small base, it's quite easy to get places. That was my horrified face. If you have a small base, it's easy to get places. So it's easy to get to this proton here, which happens to be on a secondary carbon. Maybe it's a bit more crowded than this one, but this ultimately leads to the more stable transition state and the more stable product. So in this case, the regiochemistry favors the more stable route, the more stable pathway, or the more stable outcome with the more stable transition state. Now, what's happening when we get to this guy, our friend Kotbu? What's happening with that? Comments? Huge! Enormous. Okay? So what's going to happen when we start attacking these two protons? Which one do you think is favored to attack? The one on the right or the one on the left, if the base is huge? The one on the left, right? It's going to have a more difficult time getting to the secondary hydrogen than it is to the primary hydrogen. So that means that the number, or the ratios of products start to change. And you get a shift in stereoselectivity, which is very useful in synthesis when you want to make these molecules, because you can design the reaction by choosing the base. What's happening at the bottom? If this thing is huge, what about this thing? Absolutely indescribably enormous. Beyond words. Okay? And now we've got a very nice shift in the selectivity, because now we can design our reaction. If we want the Hofmann outcome, 92% yield, we use a huge base. If we want the Zaitsev outcome, we use a small base. That's really the beginning of design, right? We're about to do a lot of design where by the end of the semester, and the 37-page final that you have to do, you have to sit there and design things using the stuff you know. Okay? You have to put all this stuff together. Not particularly easy, but fun if you can do it. Regioselectivity. Where does the double bond go based on Zaitsev rules, based on ideas of crowding? Now, without rushing through this, I've got a couple more slides and I'll break and give the exam back. Not only do you have to worry about where things happen, you have to worry about isomeric outcomes at the same place, based on stereoisomerism. The idea that in this molecule, yes, I have a proton here, which can come off. I have a secondary system, which might well be fairly crowded. I might get some SN2, but not much. I'm going to get mostly elimination. And I'm going to get elimination from here with the base going after that proton, dumping its electron density here to make the pi bond, and this bromine breaking off as a leaving group. That's fine. But that gives me two products. I get a major here, which is trans, and a minor here, which is cis. You've got to be happy with where they come from. So my major is major because it's what's the answer? More stable because of what? It's trans, as opposed to the other one, which is cis. But they're both disubstituted. So the transition state here, they both have two alkyl groups helping out. There's got to be something more to it than just that. Yes, it's over here, but let's think about this. The reaction profile for this is one step. It's up and it's down. There are no intermediates, right? It's up and it's down. So the outcome here is governed by the top of that hill. It's governed by the relative energies of those transition states. And let me say this for the first time. Or let me ask this question. Do you think this reaction is reversible? Do you think this thing can go backwards? You have a very reactive O-, swapping a fairly stable alkyl bromide for a fairly stable alkene and a fairly stable alkene, and the byproduct is this, which is where the proton went, and the Br-. So think about relative stabilities of stuff on that slide. Is that reversible? No. That's the first time we've had to make that decision. There's a lot of that to come. All right, the first time other than acids and bases. That's not going backwards. So let's go back to chapter 6. This reaction is governed by the rates of reaction. The outcomes are governed by the rates of reaction. And the rates of those reactions are governed by the height of those hills. And the heights of those hills are governed by how stable the transition states are. Okay? Ashley. I'm sorry, what does that mean? I'm going to explain that in a minute where that comes from. I'm getting there. So we have now to worry about how this happens. It isn't all to do with the relative stabilities of the products. It's to do with the heights of the barriers. It's one of those graphs from chapter 6 in which we had the possibilities. We had a kinetic outcome, a thermodynamic outcome. Sometimes they're the same, sometimes they're different. This is the example where they have to be the same. The transition state to get to this material, this product, is going to be lower energy than the transition state to get to this one. Any ideas? Less interaction, fewer interactions in the transition state to get to this guy. Think about the way this is set up. What is the relationship in a sort of a Newman sense of this group and this group? They are anti. Good. They are anti. Now, is that good or bad? Good. To get to this product over here, what would the relationship have to be for that carbon versus that carbon? Somebody said it. Gauche or eclipsed. Eclipsed. So which is higher energy, eclipsed or staggered? Eclipsed. So as we add this up, and I'm going to stop here and get ready for giving the exam back, and then I'll carry on with this on Wednesday. But that's a very subtle idea. I'm not done. I'm not, just listen, relax. You're not going to get out any sooner. Right? I might even keep you longer if you do this, just to annoy you. The whole point now is that you have to worry about places on the graph. You have to worry about the top of the reaction profile in terms of the transition state. You have to worry about the stability of the products. This is all about the top of that reaction profile. To get to here involves a lower energy transition state than the one to get to here. It's faster because the groups are over here and over here. They are anti to each other in the starter material and therefore anti to each other in the transition state, lower energy. Also, what's the molecule going to look more like? Are more molecules going to look like they're anti and staggered or eclipsed? Anti and staggered. So there are more of them. So that leads to a faster reaction. So when I come back on Wednesday, there's the graph from chapter 6. That's what we have to worry about now. Why is this reaction here for this guy? I'm sorry, let's do that again. Why is the red line, which means this product, higher, and why is the blue line for this product lower? Good chance to do some reading, think about where we are, and put that together, because this is what it is for the rest of the 2 semesters. Subtle.